Okay, there we go, I guess.
So Ricardo de Salvo again is a spectroscopist, he tells me. I first heard about him when I was visiting Cornell talking to high-energy experimenters there, and they told me about this guy. He had converted into a high-energy experiment and had spent some time at Cornell. And they told me what an interesting and bright fellow he is. And,
wow.
And then he went back to Italy. He worked, I guess, at CERN for a while. Was back in Italy and got pulled into the Virgo gravitational wave detection effort at Pisa, and was involved in the design of the very sophisticated seismic isolation system they have in Pisa. And then he was attracted here to Caltech, where he is taking the lead on seismic isolation issues for LIGO. And so, Ricardo?
Yeah, saying that this thing doesn't get there, and maybe get in there. Got stuck there. Oh, here it's coming. There. Good. Took a little bit longer to get there. So, first thing which what is for me and doesn't matter. The question is, why do we need seismic attenuation for gravitational wave interferometry detectors? We have a ground motion that is typically a micron continuously, sometimes even 10 micron. And gravitational signal is 10 to minus 18, 10 to minus 20. So one is a little bit swamped by, just slightly swamped by the ground motion. And so you need well, I am exaggerating maybe, but it's 10 to minus 10, 10 to minus 12 as an attenuation factor. And the question is, how do I fill up with 10 to minus 12 attenuation gap, and that is with a seismic attenuation and suspension system. They are typically thought as two separate systems. I look at them as a single integrated system. So how do you make the attenuation? See, I have an oscillator here. You make a pendulum, okay? And a pendulum has a resonant frequency. But if you shake it rapidly, apart from the resonance of the wire, yeah, I stole the balls from you.
We just can't see there. We couldn't see.
Okay, sorry. The high frequency vibration transmit very poorly through the pendulum. So this pendulum is a natural attenuator in 2 degrees of freedom, the 2 horizontal degrees of freedoms, and it works very well, actually, apart from the resonances of the wire that also you have to take care, but if the wire is very light, it doesn't matter really. And what it has at low frequency, if I carry it around, it just follows me at low frequency. Okay? And so at low frequency, it is flat. Transfer function is 1. If you go at a resonant frequency, and I excited the resonant frequency, just follow and have a resonance that depends on the Q, can be either low or high. And beyond the resonant frequency, it attenuates like omega square, and actually like omega 0 over omega square. So you gain in 2 ways. If you start with omega square at low frequency farther away, you get attenuation earlier. So that's important, okay? And the Q factor is important. At the end, we will discuss about that if we have time. So you gain in frequency, so it goes like omega 0 over omega square, and so you get attenuation factor paying it in frequency. And it works. I mean, if you just take a 1 meter long pendulum like this, it oscillates at half an hertz, and at half a megahertz, you get the 10 to minus 12 attenuation that you want. However, there's not much signal left at half a megahertz, so it doesn't work. Just a single pendulum like this doesn't work, really. So what you want to do is a chain of oscillators. And a chain of oscillators, you just multiply their responses. I didn't take all the resonances, only the fall-off of it. And so with 6 of those, you get an omega 12. I just put in 6 for historical reasons. So now people use less than 6 for other, okay? And that works fine. Okay, so at half an hertz, and this is, for example, true in Virgo, if you have oscillator at half an hertz, at 5 Hertz, you already get the attenuation 10 to the 12 that you're looking for. And and you have a big premium at starting at low frequency. That means making this pendulum long. And to start at half an Hertz resonant frequency, you need a 1 meter long pendulum. And then you have a big premium on making a lot of pendula. But what I described here is already a 6 meter tall chain, which is exactly what Virgo has. And it works great, but it is gigantic. And there. And this is what Virgo can do. So it has many noise levels. What is important, this one is what the seismic attenuation is 6 meter tall, 6 layer seismic attenuation chain. And if you see here at about 3 or 4 Hertz, it hits all the other noises, which is thermal noise of a luster of a pendulum that supports the mirror, and then there is a gravity gradient, which nobody knows if it is higher and lower. We will see, and then there is a thermal noise of a mirror that you heard about already. So you make up a nice chain of pendula, you think you're done. The problem of an horizontal pendulum is that it attenuates only horizontally, okay? And when you say, well, the interferometer is horizontal, so what? The problem is that every pendulum points down to Earth, and so they are not parallel. They all converge to the center of Earth, and in LIGO, this angle is 4 10 to minus 4. And mechanics of this pendula is hard to balance them better than 10 to minus 3. So you have a beautiful 10 to minus omega to minus 12 attenuation behavior, but will saturate at 10 to the 3 typically. So if you only make a pendulum that oscillates horizontally, it doesn't help you much. You have to attenuate in all 6 degrees of freedom of the body, okay? And so you want something that oscillates also in the vertical. You want an oscillating in the vertical, in the tilt, in the yaw, in the pitch, in all of them, okay? And if you can do that, you preserve this attenuation factor forever in all the degrees of freedom. So what you do, pendulum goes in 2 directions, but attached to the pendulum, there is a mass. And now this mass can oscillate in this direction, and it can oscillate in all the other 3 directions. So just making a standard mass as the bob of your pendulum and hanging it from the center of mass of the bob will solve your problems, okay? The 5 out of 6. The difficult one is the 6th dimension is vertical, because now you're working against gravity, okay? So what you want to do, you want to take something, attach it to a spring, and now this one, you see, it works very well, even vertically. I'm oscillating a lot vertically, and you see that down below it's transmitting much less, except for the resonances of this blade, of this spring. This spring has lots of resonances, and it has a lot of mass, so it can transmit lots of energy to this ball down there. A wire is much lighter, can transmit much less energy. So this spring, it's almost good, it works. But also think this massive spring is holding a little ball. If I was to attach any massive mirror to it, okay, it doesn't work anymore. So somehow we have to find, helical springs are not good enough for what we want to do. And for all of this, they have large distributed mass, they tend to rotate when it comes down, they want to be very long, and they have lots of resonances that transmit energy. So they are not good. So what people have done, have used cantilever blades. Now this blade is quite robust, you can play with, and you can hang here quite some mass, and it has relatively low resonances. This one, when it is loaded, it is flat. This is one of the Virgo blades. And Tama has similar blades, and it is good. The problem is it is also stiff, and we want it slow. We want it to oscillate a half an Hertz or below. And how do you convince this stiff blade to become soft? And the trick is to take 2 blades, you point one against the other. There are other tricks. One point one against the other, and this point, the 2 blades that are compressed one against the other tend to escape above and below. So they have a component of anti-spring, but the more I compress, the more anti-spring component I have, and by tuning the radial compression, I can balance the vertical spring constant with the anti-spring constant and get this system to oscillate as low as I want as in frequency. So how do you do? We have several examples. This one you can see, it's a reasonably big one. You put me as a scale down there to show that this one is big and it holds almost a person down there. And you can make it very small. This one is one of the small springs that you find holding directly the mirror box of Tama. There are 4 of these, and this one holds about 1 kilo each of these. So, and all the play is to move these sleds closer until the vertical frequency is as low as you want. And yes, you can do well. This one is the small springs that you have seen there, and you can tune them at 250 millihertz, even below, even lower, but what you wanted was a target, let's say, of half an hertz of oscillation to match a 1 meter long pendulum. So that is feasible. And what does a spring like this do? A spring made with in this way have a transfer function. Look, it's up to here is exactly what was the response of a spring. It is it has a resonance, and then it falls like 1/f squared. This one is the mathematical response. And then down at some point, it saturates. Over there is just the noise of a detector that doesn't see. And it saturates because at high frequency, this spring will act as a free body in space. So when an oscillation moves it up and down in here, it will oscillate around a certain button center, and the tip will recoil backwards. So what you see here is a saturation due to the fact that there is a residual rigidity and a distributed mass in the blade. And that is a function on how much you stress the material and how do you distribute it. But this is a measured setup and is an attenuation of 1,000 per layer. It means that if you, that's what I was telling you, that you essentially every layer you can attenuate a factor of 1,000 and no more passively. So what do you do with those? Well, you build a system. Here I'm showing the Tama 3 meter test towers. Tama has decided in what is 3 years from now to install a system that will look pretty much like this. This is a prototype of it. So what you see is an inverted pendulum attached on ground that can oscillate at 50 millihertz or below. Then you see here, you don't only see one blade, but this one is a free blade system for the vertical oscillation. So and then it is attached to a second filter, which also has the same sort of blades into it. So it has a second vertical attenuation, but at the same time it's also a pendulum in this direction and is a pendulum in tilt, yaw, and pitch. And then attached to that there is another box which inside contains these little springs here. These little springs are right there, okay? And they then contain an intermediate mass and a mirror and concentric recoil mass. This part here becomes very complex. This is all passive, essentially. And this part here is all complex because in here there are 2 layers of controls that allow to position the mirror in space with a precision of 10 to minus 12 meters or something like this. Absolute. And then above 10 Hertz, this system is quiet at 10 to minus 18 or plus or less Hertz. And this is what it looks in real life, just to show you. And that is when we are getting ready to send it out. And on top here, there is lots of instrumentation, which are position sensors, we'll come back to it, and accelerometers that are actually used to kill the main resonances of the system that I mentioned to you. And here is as Akiteru, who is finishing his thesis on a Fabry-Perot mounted on these on 2 towers of this kind, as he is installing it in the Hongo campus almost a year ago now, more than a year ago now. And he's just about wrapping it up now, so we'll see what it is. Unfortunately, when you have materials like this, you take a material and you hang on it, you put stress into this. Now you have many layers. You start at 10 to minus 12 meters, and then you put another layer to go 10 to minus 6, 10 to minus 12, 10 to minus 15, 10 to minus 18. You go down every time by 2 or 3 orders of magnitude in vibration. For what is a vibration comes out from outside. But this blade will be compressed. And the stress which is inside this blade will slowly release in some ways. And will produce acoustic emission. We call it acoustic emission because you put the microphone there, you hear it. Wow, metal under stress makes noise. And what causes this? This is the blade before I stress it. These one are the crystals, the grains in the metal, immediately after I stress it. And they get an uniform stress. The stress is uniform across this crystal. Okay? But now there are zillions of dislocations to this crystal. This crystal has 10 to the 20 atoms into it, and it has many dislocations. And this dislocation under the stress will, if I get excited by the thermal fluctuation, will move to the edge of a crystal and will concentrate the stress to the edge of a crystal. And then this stress material will click back. So 2 crystals inside there will click, and we can hear it. Makes this noise. Actually makes this noise. And then the other crystal will pick up the corresponding stress, so it will be redistributed. They go a little bit more in stress, and some other crystal will click elsewhere. And this one, in the springs of your car, goes on forever. In fact, after 30 years, you want to change the spring of your car because it just sits down. And we don't want that. First thing, we don't want to put the mirror down on the ground. It's an expensive mirror. And second, we don't want the noise. So while at the beginning, at the top of a tower, we could use roughly any material, as we go deeper in the attenuation sequence, we have to have better and better material, and we have to switch to materials that don't have this process here to make this noise. So, because otherwise, this will be our dominant source. And that is what, just to show that it is real, I put a microphone on a piece of blade like this, and I listen to, and this is in a matter of hours, and this is the frequency of clicks. So beginning, I get clicks at about, actually this is the inverse of the frequency, the time between, sorry, is the inverse of frequency. I should have done it the contrary. It would have been much worse if so these one are seconds between clicks. So beginning I have 1 click per second, and then after half an hour I have 10 click, 1/10 of a click, one click every 10 seconds, then 1 click every 100 seconds, and then with time my situation improves. Down there I have 1 click every 1,000 seconds out of a blade like this. And if I treat a blade like this properly, I will bring it to have no clicks anymore every day. Okay, and there are processes that we do this. But this is when already in a good blade. If I was to use the steel of your car, I would have a kilohertz of clicks continuously. And this is a solution, it's not the problem, although it has some problem at the beginning. So what is the solution that we have found here? We use special materials that are hardened by precipitation, which freeze the dislocation inside the volume of a grain. The dislocation does not move to the surface of a grain anymore. And so we stop this acoustic emission. And this is good enough for all the mechanical part of a seismic attenuation, but close to the mirror, we cannot even allow the movement of dislocation, because that also produce some other sort of noise. So we have to give up the crystalline materials altogether and use glassy materials in the mirror and the mirror suspension, like quartz fibers and quartz for the mirror, or perfect crystals. And so that is what we have to do. But let's go back at this thing. How do we freeze the material on the mechanical structure? And what did I do here? Oh, I jumped. I missed one transparency. Well, there is one missing, doesn't matter. Or maybe it is displaced. Fine. So I wanted to mention the problem of resonances. I did show you in the curve that I have an attenuation, but before attenuation I have resonances in which the mirror oscillates quite a long distance, okay? And you have, and they, the problem is that the sensors that we are using down in the interferometers have a very small dynamic range, okay? And because we have to reach very high sensitivities, 10 to minus 20 is what our gravitational wave will give to us. So even if our mass down there, our mirror, is quiet to 10 to minus 18, 10 to minus 20 meters above 10 hertz, at a resonance frequency of half an hertz, I have to keep it from oscillating in the resonant frequency. And the answer to this is to introduce somehow a damping to the resonances, okay? To stop all the mechanical resonances, so the mirror essentially stops down at the suspension point. And there are many different strategies, either inertial or viscous, active or passive. Essentially, all the experiment, all the places differ for this. I'm telling you a little bit about viscous damping, because this one we are doing over here, just at the end of the hole. This one is a LIGO stack, okay, as it is now. And this is made with springs, helical springs, that we should not use, but they have been used in LIGO stacks. And they are attached, well, in this case, it's really on ground. They normally are on a cleaner environment. And then we have intermediate masses, and there is another spring in here that you can see, and then there is an optical bench. And what is killing now LIGO is that this system resonates with an IQ, Q about 30, and we need to sense this oscillation and dump it, so that we can actually give a chance to the nice systems that you heard before to actually grab the mirror and position it to beta the 10 to minus 12. So how we studied this, we have mounted in here a position sensor, which is an LVDT, in which I have an emitter coil that emits at 10 kilohertz and two opposite receiver coils, and I read them in synchronous. And with this instrument, we can read nanometers or better than nanometer, even picometers if you reduce the dynamic range. And we put it in feedback with a forcer, a very high precision forcer that does not transmit the ground vibration. It's a derivative. It's a concept the same of a voice coil, but it has a funny shape not to transmit the residual vibration of ground. And we put these in feedback between 0.1 and 3 hertz, and we pick up the resonances of this table and then dump it. And in fact, that is what we have done recently. This one is the resonances with a damping off, and when we switch the loop gain on, you see that those resonances are damped and become very short, and the system cannot be excited anymore because it has no resonances. And we did it with 6 degrees of freedom. In other places, like in Tama, the resonances are read out from the beginning of a tower, and they are made inertially. That means that instead of sensing the position movement, one senses the acceleration of the top mass of a chain. Since the whole chain will recoil like a snake, the top always moves for every mode. So from the top you can sense all the modes, and if you use the sensor acceleration sensor at the top and the same actuator forcers here, these are the same forcers that you have seen before, you can actually damp the position of a mirror and stabilize the suspension point to the required level. And this one that I'm showing here is an accelerometer, which is a monolithic accelerometer, in which here you have a bob, and here you have two arms, one a pendulum, one an inverted pendulum. It has sensors in here, and it has a feedback, internal force feedback, and you work on a feedback to keep this pendulum stable in this bob stable inside its case. And by definition, the force that you have to do on it to keep it stable within the case is equal to the acceleration to which the case is subjected. So this one is an accelerometer which is mounted over there to dump resonances of a chain. And that is about the end of it. There is much more in seismic attenuation, but and you can see several examples of this over in the synchrotron where we have our laboratory. You're welcome to come over. And then if you have questions. Yes?
Ricardo, what happened to the idea of using a magnet coil with a frequency-dependent negative resistor?
Oh, that is...
Repeat the question.
Yes. It's an interesting idea from the Japanese group, and they just recently published the result. The idea is you can make damping very simply by taking a magnet and hanging it over a metal surface, and then you have eddy current damping, which is which works as velocity damping. However, you are limited by the fact that the biggest current that you can get into these materials are limited by the resistivity of a material. So you try to use the best conductive material you have, copper or aluminum, but they still have a finite resistivity. The next idea is you take a coil, a mechanical coil, which has an even higher resistance, but then you mount it in chain in series with an operational amplifier with a negative resistance. You put that negative resistance, tune it so you go close to zero, and then you optimize the damping of the system. And it actually, I can give you a paper because I just got it for review, internal review, final review, before they publish, and they sent it out now, I guess. Harima actually she's not here today, but she's one of the authors, so she can tell you about it. Yes?
So you showed a photograph showing the springs and masses in the LIGO 1 isolation.
Yes.
So can you just comment, are those springs then to control horizontal motions?
They are both to control the horizontal and vertical motion. Then if you look at pictures, actually...
the vertical eigenfrequencies must be very high.
That is exactly where most of the problem is, because it is 3 Hertz. Yeah, it's... actually, they are quite thick, so even horizontally they are reasonably stiff. It is order of 2 to 3 Hertz vertically, and less than order of an Hertz horizontally. And even the first horizontal in reality is sort of a pitch mode, so it's partially vertical. It's a system in which horizontal, vertical, and tilt are all messed up together. It's not diagonal by any stretch of imagination. In a suspended system, this motion and the rotation are almost diagonal.
But it's playing the same role as a pendulum would horizontally, or the same role as your candle would.
Yes. And as long as you have all of the 6 degrees of freedom, the fact that they mix, it doesn't harm too much. It harms when you try to understand what's happening and you try to control the system and dump the system. But
the glitches that you have, the sudden strain release.
Yes.
How large is the motion that induces in a LIGO mirror? Is it big enough to see in the gravity wave readout?
I never calculated for LIGO, but on also the glitches that you see are by nature fractal. They come at all different amplitude at decreasing frequency. If you have the 1% of the energy of a crystal that release, is released, and you have a 100 kilo mass, it goes down, if I remember correctly, by 10 to minus 9 meters.
So that's very big.
Yes. So one crystal that releases that energy just, so it's quite catastrophic if it happens, and that's why we developed this. We used whenever there is stress, we use this maraging steel, which has controlled these locations, and that seems to eliminate the whole problem. You have to load it, bake it. So you completely release it. We make a bake out at 80 degrees for a day is equivalent of 100,000 years of improvement. And you have seen in that picture, in which I have an inverted scale, that already a weekend was improving 2 orders of magnitude. Beginning you improve rapidly, later you improve logarithmic gain. But it can be done so that beyond a certain level, you always define it as beyond a certain level and etc. But you can say at beyond a given level, I bring the clicks below 1 times per day. That's how you do it. You cannot do differently because there is always some life into blades like this. It's not dead matter.
Other questions? Okay, so let me just say that the reading for next week, we're going to put some copies out. Paper on the web that we put on earlier this week that was provided to us by Eric Black with his lecture on it. I'll see you next week then.